So welcome everyone to today's presentation about using the CSEM. I think we have Tom, Dwayne, and Brian. Do I have it? Yeah. All three of them are going to share a little bit about how the CSEM was developed and how it's been currently used. And we've got a few more events coming up, three more under the optics umbrella. In this, one is in this series about research-based instruments. Or actually two, the one in November and December. And then in between, we've got a workshop on introducing quantum in your physics class. And then the last one, it's not really an optics one. I actually wanted to check with Chris to see if it was okay, but I guess I'll ask for permission, or forgiveness instead of permission. Yeah, so if you're an AAPT member, you could join in the coffee hour in RSVP on AAPT communities. And then Chris gave me the thumbs up, so I feel better about it. Okay, so I don't want to take up too much of your time since the hour is short. So yeah, I'll hand it over to Tom or Dwayne. Tom. Okay.
Sure.
And I'll stop sharing screen.
Okay. All right. So I'm going to try to bring up my slides and see if they'll be. So can you see my slides?
Yep.
Okay. So I'm going to talk a little bit about how the conceptual survey of electricity and magnetism was developed, and then
I'm sorry to interrupt.
Yeah.
We're not seeing the slideshow. We're seeing the presenter's view.
So you're okay with that?
Yeah.
I don't know if I can solve that problem.
Well, I mean, it's not a major problem. It's just that we see the slide coming up while you show us one.
Yeah. What if you clicked
You'll always be ahead of me.
Click the live slideshow, maybe
Yeah.
button, and see what happens there?
Yeah, use the slideshow.
How about this one?
Oh yeah. Very good. Yep, that fixed it. Thank you.
Okay, so the conceptual survey of electricity and magnetism was developed a little bit differently than a lot of the assessment instruments that are being presented during this year-long PER interest group look at assessments. And so what I wanted to do is tell you a little bit about how it was developed. And so the primary developers of the CSEM was these four individuals. So it was a collaboration between two-year college faculty and some university physics education researchers. So Kurt Hackelke at Joliet Junior College and Joliet, Illinois, and me at Lee College in Baytown, Texas, were the ones who sort of led the two-year college effort. And then David Maloney, who's at Indiana University, Purdue University in Fort Wayne, which is now called Purdue University in Fort Wayne, was one of the early PER researchers who worked with us to help develop the CSEM. It also included Ellen Van Huvelen, who was initially at New Mexico State University, then he was at the Ohio State University, and he ended his academic career at Rutgers University. But he was also a physics education researcher and had written a book on introductory physics, algebra trig based that some of you may have seen. So those were the four primary developers of the CSEM. And so in this talk, I was going to do a brief introduction, a development area, how we developed the CSEM, and and there'll be a lot of slides here, but I'm going to talk through some of them. And then the testing and refinement that we went through, and then finally the analysis and summary that we got from the research that we did in developing the conceptual survey of electricity and magnetism. So this all started, so prior to 1995, the only physics assessment instruments that had been developed were primarily in mechanics. With one exception, there was one developed for DC circuits, but it was primarily in mechanics. And so at this time, we thought that something needed to be done in electricity and magnetism. And so that's what we started off doing starting in 1994. And so we thought we could develop a survey that would assess students' concept in electrostatics and in magnetism and electromagnetism, but not circuits. Circuits was not included as part of what we had done because was already a circuit test available. So the first major part of this occurred at a working conference on introductory physics that was conducted for 6 days. It probably should have been June 18th or 24 in 1995, and it was held at Lee College. And it brought together only 9 individuals who worked on the preparation of the what would later become the CSEM. And so before the 9 people selected came to the conference, they surveyed what was available on the research in electricity, electrostatics, and magnetism. We also asked David Maloney to develop a preliminary E&M concept inventory, just sort of as a working document that we could look at and start with in our development of the CSEM. And all of this was funded primarily through a series of grants that Kurt and I had, which was called the Two-Year College Workshop Project. And so the conference purpose was to develop an electrostatic survey and to develop a magnetism survey. So it was on those 2 areas that we were developed. And so I'm going to walk through all these slides, but I'm going to talk while I go through them, and so I won't touch on every point. And so it was a 6 day conference, and we started off with having 2 different groups. There was an electrostatic group, which had 5 members, and then there was a magnetism group, which had 4 members, and we'll go through who those members are in a little bit. And each day we would meet, discuss the ideas that we were having, go off and work on developing questions, come back, present those to the other group, and then have them critique it, criticize it, make suggestions. Then we would go off and work on those and refine the questions and stuff, come back and do that again. And so we essentially did this twice every day. So our working days usually started at 8:30 in the morning. We had a lunch break. We broke for supper. We came back and worked until 9:30 or 10 o'clock at night, went back to the hotel, gathered, and just, had our post-day discussion about ideas, and then eventually went to bed, I guess. And we did this for 6 days. And so this is looking at some of the things that we did on each one of the days as we went through this process. Each day we would add in some other ideas that were developed by other individuals. Like, for instance, Chabet and Sherwood had developed a number of different ideas in electrostatics and magnetism, and we would pull some of those ideas and our development of questions. There was also some ideas. One of the participants was Marv Nelson, and Marv had developed was on the team that originally developed the capsule materials. And so he brought together some of those ideas for particularly electrostatics, but some in magnetism as well. And we continued this process through all 6 days. And then finally, we ended up with what we had thought was at least a good initial set of ideas that were in electricity and magnetism. So the 9 people that participated in this process, all of them were veteran introductory physics teachers. Most of us had 20+ years of teaching Cal-based or introductory physics, algebra trig-based, or both at our respective institutions. So this was the electrostatics group, which was Kurt and Dave Maloney. And then it had Marv Nelson from Green River Community College in Auburn, Washington, Marie Plum at Jamestown Community College from Jamestown, New York, and Myra West, who's at Kent State University's the START campus, which was one of their 2-year college campuses of Kent State University in Ohio. The magnetism, and these were the topics that were eventually developed and chosen as the core for what we were going to do in electrostatics. And it encompasses a lot of the things that we teach, both algebra and trig-based and Cal-based, in the electrostatics area. Our magnetism group included one person who wasn't a veteran teacher, who we'll be talking to you later, who was Dwayne Davian, who at that time was at Highland Community College in Kansas. And it also included Mark Bungie, who taught at San Jose City College in California, me and Alan. So it was a 4-person group working on this. And these were the magnetism topics that we were trying to develop questions for that would become part of what we would call a magnetic concept inventory. And so the result of the conference was that we did develop an initial electricity concept inventory, which was 37 questions. As we developed these questions, we also developed an answer key and a taxonomy, which would explain our best estimate of what students, if they responded to that question with that multiple choice answer, what they were thinking in making that response. So a taxonomy for the electricity concept inventory and one also for the magnetism concept inventory. Both of these were later renamed as the Conceptual Survey of Electricity and the Conceptual Survey of Magnetism. At the same time, we did create a set of open-ended questions parallel to both the ECI and MCI, which we wanted to use for testing with various student groups at our institutions to see how they responded to an open-ended question as opposed to just a multiple choice question. And so that was our development part of these initial surveys. Notice at this point, we had not come up with a CSEM. We had only come up with a CSE and a CSM. So after the conference and the first year after that, we did a number of testing at these various institutions. You'll see some of the data displayed as we run through these really quickly. A matched data set means that to those students, we gave both the pre-test and then later a post-test. And so then we would match up the results from those. In some cases, because of the way our students normally run in a course, sometimes generally we had more students taking in the pre-test than we did the post-test. So some is unmatched data and some of it is matched data. And we also started testing because we were running these workshops of two-year college physics faculty around the country. We also started testing the physics faculty attending those workshops as a post-test only because we assumed they already had initial knowledge of electrostatics and magnetism. And so you'll see some of the post-testing numbers based upon the participants at those workshops. And as we got the data back, we would reevaluate some of the questions, reword it, and make some changes as we went through. And year two, we went from a first form of the test to a second form of the test after we made some of these revisions and started testing again. And so we had a number of students that we tested at a variety of institutions, not just our four institutions, that is Lee College, Joliet Junior College, Indiana, Purdue University at Fort Wayne, and Ohio State University. Other institutions also administered these tests. And we continued to test faculty at these two-year college faculty at these two-year college workshops and continue to monitor change. And so it went through, when we met in the summer of 97, we met at David Maloney's place and did some major revision. And at that time, Alan Van Huvelen suggested that he said, it's going to be difficult for most instructors to be able to give two separate conceptual surveys in that semester that they're teaching E&M. And so he suggested that we combine those into a one inventory called the Conceptual Survey of Electricity and Magnetism, or CSEM. We could still keep the CSE and the CSM, but the CSEM is probably the one that's going to be used more often by institutions because it was a single test and it tested both conceptual domains. And so that's when the CSEM first was created. And so that was the third form of the CSEM, but the first form of the CSEM. And we continued evaluations and around the country and at various places around the nation, and sometimes even international. It was done in both Canada, Belgium, and a number of other countries, testing these out based upon people who wanted to just try these out. We also had other folks who actually helped us develop many of these things. So we got ideas from Rusha Bay and Bruce Sherwood, particularly on some of the charge problems and some of the electromagnetic problems. We also had contributions from Dennis Albers, who is the one who developed a number of circuits ranking tests, but in those they were also testing some ideas in electrostatics and magnetism that we could use. And then Glenn Julian of Miami University of Ohio contributed some ideas. Tina Lennart, who was at the University of Ghent in Belgium, where she was giving those to her large lecture classes in Belgium, made some suggestions as well, and many suggestions from the students that who took these tests, assessments in the early days, as well as the faculty members, to your college faculty members who kept making suggestions as to what needed to be changed. And so we continue that process of then some more data and stuff like that. And we developed a open-ended questions for each one of the for the CSEM that we started giving to the faculty at the two-year college workshops because we wanted to find out what they thought would be an explanation for each one of the questions that appeared on the CSEM. And that helped us refine the assessment even more. And so we continued this, and when we got to the seventh form, we thought we had finally just about came to a final version of this. And so we gave a few more examples of open-ended questions to students and faculty, and then we started doing a refinement to end up with the final product, which we thought was what we call Form H, which is the eighth form of the initial assessment instrument. And so between 1999 and 2001, we just did extensive testing both nationwide and in some cases at international institutions. We were testing it both in high school, two-year college, four-year colleges, and universities. We looked at we did primarily for algebra trig-based course and a calculus-based course, but we also had some honors courses that took it, as well as some graduate and uh, upper undergraduate courses, just to see some comparison of how students' understanding of these concepts changed with whatever level that they were in, usually post-secondary education. We also ran a quality of test items to see, to determine both the difficulty and discrimination of each one of the questions. We did a validity testing to test out the appropriateness and reasonableness of each one of the questions for both the trig-based course and for the calculus-based course. We did a reliability testing using KR20 to see how reliable the test was. And eventually that led to the publication of the CSEM and the American Journal of Physics in 2001. And so when we did the analysis of the CSEM, there were three primary categories what we looked at. One was the variations in the types of assessment instruments. Some of the assessment instruments that you've already seen in this series, when you looked at the number of concepts assessed, the number could be small, such as the force concept inventory is primarily looking at Newton's laws of motion. Unfortunately, the CSEM is testing a number of different ideas, both in electrostatics and in magnetism and electromagnetism. So you can't have as many different types of questions assessing one particular topic within a broad range of topics. And so that was one of the limitations of the CSEM that we recognized from the very beginning. There's also a language that you use in asking the questions. For instance, the force concept inventory uses a lot of common everyday language that you can present and a student can respond to that. But in electricity and magnetism, a lot of the language is technical. They sort of have to know a little bit of physics to be able to answer some of those questions. And so if they haven't had some physics preparation, they may not be able to answer those questions as well as they could if they were able to be written in common language. We tried to write everything in common language. We were unsuccessful. A lot of the questions are technical and physics based. And so they have to know some physics before they probably can answer the question. And the quality of the test items, as we mentioned, we did a difficulty on each one of the questions. I was just going to go to this real No, we better not. It's probably going to break up. So we're not going to do that. So normally you want to average difficulty of your questions to be around zero point 0.5 on a scale from 0 to 1. And so some are going to be easier, some are going to be harder, but you want them to average out to be something like that, which we did fairly well with the CSEM. And you can see that in the paper. It'll have that listed there. We also did one on discrimination where they could discriminate between certain, between multiple questions on the same topic or same idea and see how well that was pervasive throughout the instrument or the assessment. And we did that as well. We also did a validity test. We did that a couple of ways. One of them was to ask two-year college faculty during these workshops how reasonable and appropriate they thought the uh, the questions were. And so that validity test turned out to be, again, it's displayed in the CSEM paper. And as I said, we did a reliability test to see how reliable the assessment instrument was. So the CSEM ended up testing these conceptual areas. Again, for instance, the FCI tests three conceptual areas. We were doing all 11 of these. And so it was, well, we could only have two, maybe more questions on each one of the conceptual area that we could use to compare. And then we also, in some cases, was comparing, particularly for Newton's third law, both the electrostatic and the magnetism ideas, just in different topical domains. So from the paper, this was the overall result of the CSEM that where we had collected data through roughly 2000, mid 2000. And so the number of students in algebra trig-based course, the number of students in calculus-based course. Again, we did an honors course that was calculus-based, and that was well, primarily at Ohio State University. And then we did a majors, those who were in upper graduate physics majors and graduate students as a comparison. And of course, we also did it for faculty. We didn't list that here because we were interested in students' results as opposed to faculty results. Normally, the faculty ranged around 80% and sometimes higher on average. But this gives you an idea that they started at, and each one of the levels of difficulty or throughout their university career, each one of those is a little bit higher. So 25% for algebra, but trig based on the pretest, 31 for cal based, 41 if they were an honor student. I even did this in my conceptual courses but they were around 20% on pretest, so get average of guessing. Post-test, you can see that they usually increased around 20%, a little bit more for the cal-based, and a little bit more for the honors calculus-based. So the students before pre-test and post-test did increase. The CSE and CSM below it are just on the electricity and magnetism concept inventories by themselves. But what we did not distinguish is the type of instruction that was being used. So whether it was traditional instruction or some kind of innovative instruction wasn't exposed in this particular data. This is just overall, regardless of the instruction technique. Sorry, this was for, as you notice, some of these are unmatched data. So we also looked at matched data in which we actually had more data points. And these again where students who took both the pre-test and the post-test, and we excluded any students that took one and not the other. And again, over roughly 40 or 50 different institutions around the country, some of those two-year colleges, some of those university, but these are the average results, and we see roughly the same thing. Pre-test starting at 24% for algebra trig-based, around low 30s for cal-based. Post-test, low to mid 40s for trig-based and upper 40s for the cal-based. And that was consistent. If you plotted this on a graph that was sort of like the Hake gain graph that Hake did on his original paper, then this bottom line is if you see a 15% gain between pre and post test, the middle line is like 40% gain between pre and post test, and the top line is 60% gain. For mechanics ideas, particularly like the force concept inventory, Hake would claim that to become a Newtonian thinker, you had to have a 60% gain. Well, that doesn't happen very often in electricity and magnetism ideas. Well, we have one data point at which it happened. We do have some that made it above 40%, but we have a bigger cluster who made between 15 and 40%, which is what we were seeing on our average. And then some that had less than that. So our results were really discouraging. We could pinpoint some certain topical areas that were more discouraging than others. And in the paper you'll see each one of those topical areas written out with explanations of what we had found. Students have trouble with electrostatic ideas, particularly if there's any somewhat level of shielding in their minds that's involved. They have trouble with understanding how to deal with those. But they even have more trouble with magnetism and electromagnetism ideas. Some of them have been exposed to electricity ideas previously before they entered our courses, but only a few of them were exposed to magnetism ideas unless they took a course, a high school course that involved electricity and magnetism. And so our next step was, well, we needed to probably come up with a better assessment instrument that had more testing and more student response, and where they went through an actual interview protocol with students. We didn't do that. We got results from students. They answered questions as well as the assessment instrument. And so that's how we built our particular uh, ideas associated with the assessment. We did collect a bunch of data afterwards only because people kept sending us data. Whoops. And so the numbers aren't remarkably different. And so the numbers, and we actually got numbers after 2008, but I quit collecting the data because there was other people who were doing this at various sites around the world. And so it was more important to look at their data than, more accumulated data from us. So that's the development of the CSEM. And so I'm going to turn it over to Brian, who's going to talk about what he does in his program at Seminole State College. Oh, is there any questions on my part before we go on?
I know, Kareem, you had a question about like translations. Did you want to like get the
And
answer to
Kareem,
that now or?
I don't know whether it was in French or Flemish, but I think, Ghent is more in the Flemish area. In fact, I am sure
Yeah.
Ghent is more in the Flemish area. So I believe that it was in Flemish.
So, but at this point, though, there are multiple translations. I would imagine that it's been translated into Spanish. No, has it?
Nowadays, yes. So
Okay.
now the CSIM has been translated into, I don't know, at least 6 or 8 different languages and probably more. But
Yeah.
there's, I think on the Fisport site, it'll have like 4 or 5 different language versions of the CSIM, but I'm sure there's more than that because we see papers that appear
Mm.
that's from countries that aren't one of those languages that are used.
Okay.
Yes, when you were young at the time, big deal. Anything else?
Tom, I had a little question for you. So I would imagine that the flavor of the revision suggestions probably evolved over time as your forms matured. And so I was wondering, what does that look like? What were some of the typical types of revisions you saw when the forms were early? What happened when they got later? And were there types of revision suggestions that came up that you found, oh, we don't usually incorporate those kinds of suggestions?
So to answer that in part, Brian, so for instance, the initial CSE was 37 questions, of which 20 questions were pulled on the CSEM. So as we went through this process, a lot of it, sometimes it would be syntax errors, but mostly it was grammar errors. And then, this may be a better answer based upon what my students have told me for this question. And so some of the answers would morph a little bit based upon what feedback we got concerning typical student responses to this question. And so, but a lot of it was of that nature. There were some questions that were obviously dropped. There were some questions that were combined so that we could get it down to, well, 32 questions for the CSE, but 20 questions used in the CSEM and electricity. And the same was true for magnetism. Although there was probably more changes in magnetism only because, excuse me, the initial results from the magnetism questions were so bad that, we really had to work those questions, I think, carefully to try to make them a little more understandable for students to read and understand. We weren't making the questions necessarily easier. We were making the questions more readable and understandable to the average student, which was what many of the instructors was telling us, not to change necessarily responses or answers, but to make them more understandable. Because unfortunately, they use a lot of physics terminology and not common language terminology.
Has anyone tried the CSEM on maybe a higher level course, maybe let's say a junior level physics E&M?
Yes. And so that's what that data line concerning, well, it's probably in my data, but it was given to some junior, senior level students who were taking whether it was the junior level or the senior level E&M course.
Mhm.
And it was also given to some students who were taking the graduate Jackson type E&M course.
Mhm.
And there was usually a slight increase in each one of those. But so in other words, if they were taking the junior senior level E&M course, they wouldn't score at a pretest of 30 or 40%. It would be more in the order of 50 or 60%, certain, but not 80 or 90 or 70 or 80%. And the increase from pre to post test, and there was limited numbers for this, was always more like 10% or 15%. Um, we we didn't see very many classes approach 80 or 90%. And again, we didn't see very many classes at whatever the level have a hate gain that was above 0.6,
Yeah. All right.
except for maybe one of the presenters who's going to talk in a few minutes.
Oh yeah, that one, of course.
All right, is there another new one? Yes, it was given to grad students.
Yeah, okay.
Any other questions for me before we go on to the people who are actually using it in their programs or courses now? I mean, I did until I retired, but I did retire.
I'm sure if you think of some, we'll probably have some time at the end
Yep,
if we
I'll
need
be
to
glad to
look back
answer
at Tom.
any as we go through.
Yep.
So, Brian,
Yeah. So I presented last month on our department using the force concept inventory. And so this is kind of the companion presentation to that with the same sort of results, but for the CSEM. So just for background for those who weren't at my presentation last month, our department agreed that we should track performance on concept inventories for all of our physics classes. And this is for our 5-year plan at the college. And we want to be able to see whether any interventions that we're making are actually helping our 2-year college student population. And there isn't as much data on 2-year college performance as there is on 4-year university performance. So we're contributing to the pot here of how these concept inventory scores are faring for the 2-year college population. So the way that we did it was in our Canvas learning management system. I programmed in the concept inventories as Canvas quizzes. And Canvas dumps out the data in a format which isn't immediately usable with the Phys-Port Data Explorer. So I had to go and write a script to ingest the data into the Phys-Port Data Explorer website properly. I also have consent forms, IRB consent forms, because the entire college is doing projects in some form or another to see if we can improve student learning. And so I have matched not only the pre and post data, but I've also matched up the consent forms. So I threw away anything that didn't have both pre, post, and a consent form. And as a result, I wound up getting just around 50-ish results for the CSEM per semester. So that's on my next slide here. We've been running this for 1 year so far. So fall 2024, spring 2025, we're running it again this term. We have a whole lot of engineers who need to take physics 2, not as many other people who need to take physics 2. So not very many classes of algebra-based physics 2 have taken it. And here are results from the fall term. These are the scores for the pre and post test on the matched students. And so the algebra-based pre-test is over here on the left, the algebra-based post-test physics 2 over here in the middle, and then the calculus-based pre-test here on the middle right, and the calculus-based post-test here on the far right for fall 2024. And also off of Physport Data Explorer, they've got the 2-year college nationwide averages. So the post-test average here off of Physport Data Explorer at 36% score, and the pre-test average at the 22% score here. So there aren't very many numbers, only 7 students here in that algebra-based cohort. So the error bars are really, really big on that. The calculus-based error bars a little bit better. Overall, things are looking not too dissimilar from the US averages there. But one thing I had found when I looked at the Physics 1 students and the force concept inventory was that the pre-test scores and the post-test scores seemed to be better if you had more preparation. So the interesting thing to look at is, do the Physics 2 students have that same effect? I don't really have the statistics to say for sure about the algebra-based, but if you go and you look at the spring results, then you can see that I definitely don't have enough statistics on that algebra-based class to see yet whether they are consistently lower in score because of the lower preparation level. In fact, in the spring 2025 results, it looks like you might even say that the algebra-based cohort of 14 people had slightly better scores than the calculus-based cohort of 66 people. So jury's still out there, I think, because of the low number statistics. I did also administer the CLAS to our physics sections for all of our full-time faculty. And so we looked at the students' attitudes and whether they aligned with what expert physicists would say about solving a physics problem. And so the score on the CLAS indicating how well students agreed with what an expert would say, that's along the bottom here, and the CSEM scores on electricity and magnetism along the vertical axis here. And you can see that there's a mild correlation there between the CSEM results and the expert-like thinking results. And that's about what the other papers I found would say, that there seems to be only a mild correlation there in most cases, although it's variable. Some papers say, oh, there's not much correlation between expert-like attitudes and actual test scores, and other papers say there's more of a correlation. In our 2-year college population, we got a weak correlation there. And then, of course, you might want to look at the normalized gains instead of the raw scores. So this is the same graph as 2 graphs ago, but it's plotting the normalized gains instead of the raw pre and post scores. Again, low number statistics on the algebra-based cohorts, so it's hard to tell for sure whether there are any trends in gain with preparation level here, but we'll gather some more students here and see if any interesting trends emerge. And so that's all the data I had to show here. And If anybody has any questions, I can take questions now, and then Dwayne can also set up to show us his results.
Well, I think it's surprising, Brian, that even though again the numbers are small, but we always have small numbers, uh, and an individual course, that the spring algebra trig-based course did such a remarkable improvement.
Yeah, that was definitely interesting to see, and it shows that even with a lower preparation level, you might be able to get higher gains out.
Yeah. So one other question, was there any instructional difference that you know about between these uh, during the fall and spring, whether it's algebra trig-based or cal-based courses?
These sections were taught by our full-time faculty, almost all of them, and we're all pretty much in agreement that we want to use interactive engagement type techniques. So most of these scores are going to be interactive engagement in the two-year college population. Of course, if you look on the Physport Data Explorer and you look at the averages it spits out for the two-year college population, versus the all student population. The two-year college population does get average lower scores on the CSEM than the whole population, including the four-year universities.
Mhm. Thanks.
Yeah, I was just asking because I'm assuming like any instructional difference are going to be swamped by the fact that, if you take physics one in spring and then you wait a summer to take physics two, that's probably very different than, waiting two weeks between fall and spring.
Any other questions for Brian before I start talking?
Well, a quick one for Brian. Can we maybe at some point also look at the correlation between the FCI and CSEM? Because we have the same cohort of students. I think we can probably match the students who from one semester to, especially like the fall, spring, that sort of thing. I mean, you have the data, so I'm sure if you can look at it maybe at some point.
Yeah, I will have to write another script to do matching between terms, but that's definitely something to look at is the effects between terms. We've not done looking at how the FCI and the CSEM change between terms for the same matched students yet, but we did notice on the CLAS scores that not matching students, but just looking at the classes that you would think that the physics one students moved into, that the CLAS scores actually drop in that 2 weeks between the classes.
Yeah.
Okay.
All right. Well, I guess I'll get
That's
going
your
then.
cue. Yeah. Yeah.
Couple things. Like Brian and his institution in Seminole, we've agreed at my EMCC to all give FCI for our algebra trig-based and calculus-based first semester, CSEM, and our second semester calculus-based. Because of logistical reasons around here that almost everybody has quit requiring the second semester algebra trig-based, like all the pre-pharm, all the medical schools around here have ceased to require the algebra trig based. We haven't offered the second semester algebra trig based in 3 years because we just didn't have a population taking it anymore. And those that were taking it were taking it one of our sister colleges that was offering it online. And I'll just leave it that there and move on from that. I'm going to approach this a little bit different than Brian did because I want to approach how I actually use the scores I get and the answers I get to try to, and particularly on the pretest, to try to guide my instruction. Okay. So just as a reminder, let's see. Oh, come on. You can do it. Why are you not showing up? Oh, all right. All right. This was the pre-test, post-test that data that Tom shared. Okay. Now, this is not just for community colleges. This is for um, all levels of 4-year and so on. Okay. here's EMCC's, in particular mine, because I didn't want to, I didn't have permission of my colleagues to share theirs, but it's a little different, but not a ton. So here are my results for the last 7 years. Okay. Now you notice my pretest is a little bit lower, okay, than the national average on what Tom was presenting. Post-test is a little bit higher. But I think I'm going to attribute that not because of anything I'm doing particularly well in the class, but how I approach what I do with this pretest data. Because once I get that pretest data, I spend a solid week doing nothing but combing through that and deciding how I want to do the semester. Okay. And that is a little bit unusual in probably how I approach it. So, one of the things I particularly do is spend a lot of time specific individual question. I go through and I do this for the force concept inventory too, when I'm teaching mechanics. And I look at the distribution of not scores, answers on each individual question, looking for patterns. Is it random guessing? Is it a very specific misconception that they all seem to have? Because random guessing, that means they don't really have conception. It's easier to change. Okay. If they're all got 24 students all answer the same wrong answer, that's even more interesting. And my cat's deciding to make an appearance here. So this is Sheldon, everyone. Okay. Um, sorry, Sheldon. In particular, one that is interesting that I do want to emphasize is you were asking about the correlation between first semester and second semester, FCI and CSEM. One of the things you can look at is Newton's third law questions on the CSEM versus how they did on Newton's third law on the CSEM versus the FCI. And you're going to find, unfortunately, that they don't believe it when it comes to magnetism and electricity, at least coming in. Because again, it's a different context. And so Newton didn't have anything to do with electricity and magnetism. So therefore, of course, it doesn't apply anymore. Okay. Which is unfortunate. And then postmortem, how they change by question. So in other words, the key at the end of the semester is then to say, okay, they had this distribution of answers at the pretest and this distribution of answers at the post-test. What did I do to make that change or not make that change? And so I spend another 2 weeks after each semester really looking at that question by question. So I was mentioning this one about ones that in particular are Newton's third law. This is a great example of ones that are very nice to look at and see whether they actually believe it. Because they start off with, okay, you have these two objects, there's same forces on each other. Then they make one 4Q, 4 times as much charge. Okay. What happens to the force on each one? Okay. Do they believe it or not? Okay. This next piece about whether they're further apart. That's a little more challenging because you actually have to know Coulomb's law and the R squared functionality. But honestly, I'm happy if it's gone down. Okay. Because if they even realize it has a spatial difference, I'm okay with that. Okay. Another one about Newton's third law. Okay. Whether they believe the current carrying wires have forces or not is interesting, but you don't see answer E. Okay. At all. They all believe, whether it's because it's just the way the problem is worded or not, they all tend to say that there is some form of force between these two. And of course, the 3I puts much more force on the I than the 3I, even though they have no idea what that I necessarily means, but it's bigger, so therefore it's bigger. Okay. And it's sad, but it's true. Okay. So one of my favorite ones, and Tom mentioned giving this to a bunch of workshop participants. And I remember one of my favorite when I went to one of those workshops and the discussion about this question in particular and the arguments about this question and people arguing with each other about what the answer with this one is. Things like this are very challenging and you get really interesting results from your students. Okay. I honestly expected when I first started this process of actually looking at individual questions, I expected this to be just kind of a random, okay, 20% on each or some small variation of that. It is not what I saw. Okay. The students had definite ideas about this, but it was not what I expected. Okay. By the way, the most common answers, at least for my students, are A or B. Okay. They don't think there's anything happens, or B, which I would have expected also a lot of C, but I just don't see that typically. And I don't have a good answer for that, but that's one I'd love to interview some students on why they do. But there's a limited amount of time. So, like Brian, okay, I do look at the results. I do look at these things, but one of the things that I do is here's what I look at when I get the pretests. Okay. So this is actually from this fall. Okay. So I just pulled out some fall data just as an example. Okay. So I look at this. So looking at the top data, what do you notice? And this is an open question for all of you about this response pattern. By the way, this asterisk one is the correct answer.
A lot of people picked detractor number 5 on the first question.
They sure did. Okay. It's a pretty strong rate of picking the wrong answer. Okay. And it's the same wrong answer. Okay. Versus what you see on number 2, the second one I have here, which is a much more even distribution, even though it's a much lower correct rate. Okay. But it is a much more of a random guessing looking thing, but a slight agreement that 4D, okay, the way our system, our Scantron reader does them is they turn A, B, C, D to 1, 2, 3, 4, 5. So that's what you're seeing there. But I spend the time going through and saying, okay, by the way, which of these is harder to deal with from an instructor standpoint, the top set of data or the bottom set of data?
Top.
And I have my opinion, but I'm curious about
Yeah.
yours.
I would say the bottom.
The top one, I think, because they're all dead set on one answer, and you're going to need to fight that.
But I'm having to fight only one idea.
Yeah, yeah, but it's well entrenched.
Yeah, but I think you would probably be able to know why they chose 5 in the first case, but maybe a bit harder to parse why they chose the other answers in the bottom case.
It looks like they're thinking in the first one. And the second one looks like they're guessing.
Yeah, it very well could be. And again, that makes it harder to deduce and how to decide. But one of the things that I have found that really helps my students conceptually is when I spend the time on this pretest data, looking at this and trying to come up with ways. Again, I'm not trying to teach to the test. They will never see anything that looks like the test question again until the post test. But conceptually, how can I address some of these things via tippers, via ranking tasks, being different types of questions, different ways to approach it to try to get it this obvious misconception that they have in number 5. Okay. For 65% of the students saying that. Okay. Does that make sense to everybody? So that's one of the things I really do. And that's all I really wanted to share because I wanted to focus on, again, that one of the things, if you're doing any of this, what Brian's doing, what Tom did, is the more you utilize the data, okay, to actually help direct your instruction, that's the single best way I have found to actually get the improvement you want. But I will tell you that is far and away the hardest part, in my opinion, because it takes the time, it takes a lot of thinking, and to be fair, it takes a lot of guesswork because, you know, Prim and Anthony said 2 different things. Which one would be easier to deal with? Sometimes everybody answering the same wrong answer is very easy to deal with. Sometimes random guessing is easy to deal with because they don't have any answers, but it's not consistent, and that in its own right is hard.
And I mean, do you see also consistency from one semester to another? Okay.
I do. And one of the things that's interesting is that by looking at that, that's one of the other things I kind of track. And is there anything we're doing in our mechanics class affecting what we see going forward? Okay. And one of the things that we've tried this fall in the mechanics classes is actually doing a couple of electrostatic type problems to discuss via Newton's third law to see whether that will impact when they take the next class or not, doing that longitudinal study piece of it. So ask me again in the spring, and I'll have a better answer for that one.
So I have a question and then a comment. So I guess the question would be kind of like to everyone, talking about how you maybe leverage the assessment data, and Tom brought up having these open-ended questions, at least in the development phase, and then you mentioned student interviews. I'm just wondering, like, do you see these like maybe supplementing the test with open-ended questions, or maybe like selecting a couple of students to like interview and ask them why? Like, I know you said it's a lot of time, but could you imagine like scaling it some way, like to reveal some things? Oh, sorry, Dwayne, you're muted.
Yes, I have. I actually do interviews with all of my students as one of their tests, their celebrations every semester. Um, and they do get these kind of questions that they have to explain and explain their thought process to me through the whole thing. And it's usually their next, not their final, but their last midterm, where they come in with a 20 to 30 minute, depending on the class, period with me, and we go through a series of questions and we have to talk and discuss. And in one regard, it's much easier for them. In one regard, it's much harder for them. Why is it harder? Well, there's no faking it and just being able to pretend you got the equations and get out of it. But the nice thing is it allows me to probe deeper and say, okay, you're missing this piece. What if I gave you that idea? Now what can you do? And so it allows them to get a kick in the middle of their test, if you will, and be able to get further than they might have otherwise on a standard written test. But the hard part is then to have enough questions to compile to actually do something like these concept inventories do.
And then Tom, do you see like a role for like the open-ended questions that maybe you kind of had during development to do something like what Dwayne, maybe not, as the same as an interview, but could you have an open-ended question to maybe reveal some things?
We certainly could have, and I'm not sure. Well, I am pretty sure why we didn't do it, because most of these we didn't have uh, an easy way of doing it. So Alan and his classes at Ohio State were teaching to 250 students or more, but that was just he couldn't have done this unless he wanted to do student interview protocols, which he could have done, but he didn't. Uh, we didn't feel comfortable with that because we didn't develop the techniques to do that, or the questions, or the protocol to do that.
And sorry to interrupt while you were answering my question, Tom. I'm just putting
Oh,
up the QR code for the feedback slide for those of you who can offer feedback for today's event.
I got another question for Dwayne. So you mentioned the fact that the student will not see questions of that type until after the post test. How do you get at trying to get them to work on this notion of the third law without activities or questions or exercises that, in a way, ask the same question about proportionality or relationship between the two forces and so on?
Yes, I'm not saying they don't see questions that address it, but they're not going to see the same question. And I'm not trying to do anything that necessarily exactly resembles. Okay, so one of the things that I teach, and I'm not going to go too deep into this, is the idea of a system schema where we're describing what's interacting with what. We actually frame Newton's third law in terms of interactions. But then when they make a system schema for a charge situation, okay, get them to actually start thinking about what that meant. It's this one's interacting with this one, and thus Newton's third law described
Mhm.
the interaction between objects. So kind of hearkening back and bringing them back into that and getting them that way without necessarily saying, okay, this one's 4 times as big. This one's only 4 Q, 4Q, how do they compare?
Hey, Tom,
I'll
wondering, we're thinking about next term adding some inventory on circuits. Any favorites?
Well, I think later in the spring, I think aren't y'all doing one on the direct?
We are, that's the plan,
Yes,
yes.
yes, that's
And
in
so
it.
that was the original one, well, maybe not the original one, but certainly one of the first ones developed that was widely used. So you may want to look at the direct as an assessment instrument. Dwayne, do you have another one that you think is better than direct?
Oh,
Muted.
Dwayne, you're muting.
Yeah, it's the one we use.
Okay. How robust is it? In terms
It's robust enough for, in my opinion, for a second semester physics class. It is not robust enough for an engineering circuits class by any stretch of the imagination.
okay.
So just in the interest of time, I don't want to cut off the questioning, but just because it's 3:01, just want to maybe let people know just in case they have somewhere to go. And I'll leave the QR code up and with the link just in case anyone needs to catch it before they go. And yeah, if there's any questions, uh, maybe you could stick around for a few minutes, but just in case you do need to go, just to be cognizant of the time. And but thanks to Tom, Dwayne, and Brian for being willing to present. And yeah,